In this section of Chapter 4, I would like to discuss molarity calculations and dilution problems. First, let me define what molarity is. Molarity is a unit of concentration. How is it defined? Moles of solute divided by liter of solution. So once you know what you're adding to, say, aqueous solution, that would be the solute, and you calculate the moles of it and divide that by total volume in liter, and that would give you molarity or concentration of that particular solution. As an example, let's go over number 69A, page 153. In the next slide, I'm explaining to you how to do problem like 69A. So in this problem, in 69A, they're asking which will have the highest concentration of potassium ion. So basically they're asking for concentration of potassium ion and highest. And the samples they wanted us to examine would be 0.20 molar KCl. So let's write down those. 0.20 molar KCl, 0.15 molar K2CrO4, potassium chromate, and 0.080 molar K3PO4. So when you make a solution of these compounds in water, keep in mind metal is going to come out, potassium is going to come out. So how much potassium plus I'm going to get from 0.20 molar KCl? From each KCl, that'd be 1 K plus. So from 0.20 KCl, it'd be 0.20 K plus. So concentration is going to be 0.20 molar K plus. Now the next sample. In the second sample, we have 0.15 molar, and each such molecule would have 2 K plus. So if I have 0.15 molar, for 1 molar it'd be 2 K plus molar. Okay, now in this case it's going to be 0.15 times 2, because for each molar concentration you'd have 2 molar K plus coming out of this compound. So this gives you 0.30 molar K plus. In third case, from each molecule of K3PO4, you're going to get 3 K pluses. So from each mole of K3PO4, you're going to get 3 moles of K plus. If it's 0.080 mole, you're going to get 3 times 0.080. So 0.080 times 3, that's equal to 0.24 moles K plus. So they're asking for, in which case you have the highest concentration of K plus. So answer is this one, 0.15 K2CrO4. Make sure you understand that. You'll always have to find out how many K pluses are coming out from each molecule. Here we are showing you how to make a solution of known concentration or known molarity. You can weigh out the solute. Of course, you first need to calculate how much solute mass you need and also find out in what volume, and then you make a solution to get the kind of concentration that you'd be you'd be trying to make. That's one way of doing it. So adding solid to water and then make a solution. You can also make a solution from a concentrated one by adding water. So basically you take a small amount of concentrated solution. Of course, you need to calculate ahead of time how much of concentrated solution you need to take and how much water you need to add to get the desired concentration. And that's how you can also make a solution with known concentration. Most of the dilution problems deal with expression like these: molarity times volume. Let me tell you what you're really getting when you multiply molarity with volume. Molarity has the unit of moles per liter, and the volume has the unit of liter. So molarity per liter times liter gives you moles. Now, keep something in mind. If initial molarity and initial volume gives you initial number of moles, that would be equal to the final moles if you're not adding any extra moles during the solution process. And I'm going to explain it further in next couple of slides. So keep this in mind. Initial molarity is going to be equal to final molarity if you are just adding water to make a diluted solution. Here we are explaining that more clearly. If you look at the figures, I have 3 solute molecules in water. Just to make it simpler, I wrote down 3 there. What we're doing is we're adding water. So the volume has increased. So obviously concentration is going to decrease because moles per liter, remember the concentration unit is moles per liter. So volume is increased, so liter is increased with the same number of moles, so concentration is going to decrease. Even though concentration is decreased, look at here, number of moles of solute did not change. Now in this kind of problems I can apply this expression: molarity 1 times volume 1 equals to molarity 2 times volume 2. What that tells you, initial mole equals to final mole, and that's the case in these cases. That means my dilution process did not change the mole of solute, and in those kind of cases you can set molarity 1 times volume 1 equals to molarity 2 times volume 2. This is the second kind of dilution. In this case, you're not only adding water, you're also adding little extra solute molecules. So in that case, you can't use this expression because molarity 1 times volume 1 gives you moles of solute at the beginning. You cannot set it equal to moles of solute at the end because, as you can see clearly, your moles of solute has changed. So in that case, you can't use this expression. So be careful before you use this expression, molarity 1 times volume 1 equals to molarity 2 times volume 2. Make sure that dilution process does not change number of solute. Let me now go over problem number 72C, page 153. The question is, when 3.60 gram, let me write down that, 3.60 gram of KCl, 3.60 gram of KCl is added to 75.0 ml of 0.250 molar calcium chloride. So basically you're adding 3.60 gram of solid potassium chloride in 75 ml of 0.250 molar calcium chloride solution. Now you need to find out concentration of each ion in this solution. So basically they're asking for concentration of K plus, concentration of Cl minus, and concentration of calcium 2 plus. So these are what we need to calculate. Now you know that molarities are the concentration units, so we can't deal with gram. So let's change that gram to mole. So you already know that how do I change from gram to mole. So start with 3.60. So 3.60 gram KCl, gram mole periodic table. So look at periodic table for masses of K and masses of Cl, add them up, and this is what I got. 1 mole KCl divided by the gram of KCl, which would be 39.1 is for K and 35.5 is for Cl. And that would be the gram of KCl. Now this gives you moles of KCl, and I got 0.0483. 0.0483 mole KCl. Now the volume is 75 ml because solid was added to 75 ml of calcium chloride solution. So what is the concentration in molarity? So molarity of KCl, let's write down that, KCl will be given by moles of KCl divided by the liter. So we already got moles 0.0483, 0.0483 moles, and we know it's 75 ml. So change it to liter, divide by 1000. So that's why you get 0.075 liter, and this gives you 0.643 moles per liter, or capital M. That's the net concentration of potassium chloride in the solution. Now keep something in mind, that potassium chloride in water is going to break down into potassium plus and Cl minus. Same would be the case with calcium chloride, that would break down into calcium 2 plus and 2 Cl minus per molecule of calcium chloride. So let's find out how much potassium plus we're going to get from KCl. So let's write down here the concentration of K plus, which is only coming from KCl. So it's kind of straightforward here. Now 1 molecule of KCl would give you 1 K plus. So 0.64 would give 0.64 K plus. So that's 0.643 molar would be the concentration of K plus. Now Cl minus, that's coming from KCl, would be the same amount. 0.643 molar. Again, is for the same reason. If 1 molecule of KCl would split into 1 K plus and 1 Cl minus. So when 0.643 moles split, you get 0.643 moles of K plus and 0.643 molar Cl minus. So that's all you get from KCl. Now let's find out what we're going to get from calcium chloride. 0.250 molar calcium chloride. So first write down that 0.250 molar calcium chloride. Now that breaks down into calcium 2 plus. Think it this way: if 1 molecule of calcium chloride breaks down, you get 1 of calcium. When 0.250 moles break down, you get 0.250 moles of calcium. So calcium 2 plus concentration is going to be 0.250 molar. What about Cl minus? Cl minus concentration should be 2 times that of calcium plus, because from each when each molecule of CaCl2 breaks down, you get 2 Cl minuses. So when 0.250 molar breaks down, you get 2 times 0.250. So let's write down like this, 2 times 0.250. And that gives you 0.500 mole of Cl minus. Now we already got two answers here. K plus we already know in the solution would be 0.643 molar. Calcium 2 plus would be 0.250, but Cl minus came from both calcium chloride as well as KCl. So you need to add those two quantities. So let's write down here that Cl minus, net Cl minus will be given by Cl minus will be given by the sum of these two numbers, 0.643 plus 0.500. And that gives you 1.143 molar. So these are my three answers, all highlighted in green. So K plus is 0.643, calcium 2 plus is 0.250, and Cl minus is 1.143 molar. Let's go over number 75A. In question, they're asking you to make a sugar solution or sucrose solution. The formula is C12H22O11, and they want you to make 250 ml. Let me write down that. 250 ml, and the concentration is 0.250 molar sucrose. And sucrose, they gave you the formula for sucrose, which is C12H22O11. So the question is, how do you make it? Now, first we need to find out how many moles of sucrose I need in that volume. So let's find out. Now, 0.250 I can write down as moles per liter. So 0.250 moles. Now I'm going to write down the volume moles per liter. That's C12H22O11, H22O11 times the liter, because that gives me the moles that you need to add. Now I have 250 ml, so divide by 1000, so that would give you 0.250 liter. 0.250 liter, and that gives 0.0625 moles C12H22O11. So that means you basically need to add that many moles of C12H22O11 in water to get 0.250 molar solution. Now we need in gram, because that's how you weigh a substance. So let's now calculate from moles to gram. I believe you all know by now how to go from mole to gram, mole gram periodic table. So I'm just going to show you how to do it, then you can get the final answer, 0.0625. That's moles. C12H22O11. And I need to get gram of that. So gram of C12H22O11. Remember, we're looking for gram-mole relationships. That's mole of C12H22O11. Now, you can readily calculate mole gram. Have a periodic table in front of you. look for mass of carbon, which is 12. So that there are 12 carbon atoms, so 12 times 12. Then there are 22 hydrogen and 11 oxygen. All the masses need to be added here. So that's how you get the gram of C12H22O11. And once you figure out this, that would give you the quantity of sugar that you need to add. So that gives you gram of C12H22O11. So I would like you to get this number, and that would be the final answer to this question. That means this much sugar or sucrose you need to add in 250 ml of water to get 0.250 molar solution. Now we are going to do number 75b. In 75b, again, they're asking you to prepare a solution which is 350 ml of 0.1 molar sucrose. So let me write down what they're asking for. So they're asking for 350.0 ml 0.100 molar sucrose, which is C12H22O11. C12H22O11. Now they gave you a more concentrated solution. So let's have a mental picture of this, how to make it. This is the concentrated solution in the bottle, and they have 3.0 liter. And the concentration is 1.50. 50 molar. Just by looking at the molarity, I see that it's the more concentrated solution. And we know how to obtain dilute solution from concentrated. You take a little bit of concentrated solution. So let's draw. You take some solution, a small quantity of that concentrated one, let's in the bottle, and then rest would be water to get the final solution, which would be 350 ml. So the question is, let's call this one V1, a small quantity that you get from concentrated bottle. So this is the concentrate solution, more concentrated solution is in that bottle on the left hand side. Okay, so our first step would be to calculate the volume that I need to pour in from the 1.50 molar bottle. Now keep something in mind. Your initial volume is V1. Do I know the initial molarity? Yes, because this solution is coming from the bottle with high concentration, which is 1.50 molar. So I do know the initial concentration, which is 1.50 molar. Do I know the initial volume? No, I need to figure out that. What about the final volume? Yes, final volume has to be 350 ml, 350.0 ml, and final concentration they gave you, because that's the intended concentration, 0.100 molar. Now, can I use M1V1? Yes, because in this case, solid did not change. Amount of solid did not change because you just added water to dilute it from concentrated solution to dilute solution. So I can safely use M1V1 V1 equals to M2V2, as amount of solid did not change during the dilution process. Okay, now let's plug in all these numbers, and don't forget that I need to plug in these numbers, like M1, molarity 1 is 1.50, volume 1, we don't know, we need to calculate that. Final molarity would be 0.100 molar. Final volume 350.0 ml. Okay, now we need to solve for V1. And if you solve for V1, it's a simple algebra. What I got is, you can write down the setup if you want. 0.100 times 350, 50.0. This is molarity, this is ml. And at the bottom you have 1.50 molarity, and you can see that they would cancel out. The molarity would cancel out, so this answer would be in ml, and that value is 23.33 ml. What this tells me, that I need to take 23.33 ml from the bottle that has 1.50 molar concentration and add rest water to get 350 ml. So how much water to add? So let's write down here. Water to add. So take 23.33 ml and you need to add water so that the whole volume becomes 350. So 350 minus 23.33, and I'd like you to get this final answer. So basically you take 23.33 ml of concentrated solution and add water to get 350 ml. We have some measuring cylinders or bottles which have the capacity of 350 ml. So it'd be a lot easier to do this kind of experiment using one of those containers. So you add 23.33 and then add rest of the water to get 350 ml.